All right, picture this. It's 8 a.m. on a Tuesday morning at a massive transit hub, something like KL Central. You're completely surrounded by thousands of rushing commuters layered across these deep underground subways, ground-level bus interchanges, and elevated rail platforms. It really is a marvel of modern infrastructure. But hiding right there in plain sight behind the architecture is a complex, fully automated guardian designed for one specific, truly terrifying scenario. Welcome to this explainer. Today we're going to decode the engineering marvel that actually keeps you breathing when disaster strikes underground, the Intelligent Hybrid Smoke Management System.
Okay, let's dive into this. Imagine an electrical fault sparks a sudden fire on a packed platform. Or maybe a massive stack of luggage just goes up in flames in the main concourse. In a space this incredibly dense and confined, what is the actual mechanism keeping thousands of people from getting trapped? How does a building practically fight back while everyone inside is desperately trying to escape?
To understand the solution, we really have to recognize the true villain here. Yes, the flames are dangerous, absolutely. But as experts warn, smoke is the primary hazard. It moves exponentially faster than fire. It blinds people, triggers overwhelming panic, and causes this asphyxiation way before the actual heat of the flames ever reaches them. Basically, if we can't control the smoke, we cannot save the people.
And the fascinating strategies we're unpacking today are actually pulled directly from an incredible engineering case study produced by the Department of Chemical and Environmental Engineering at University Putra, Malaysia. They've outlined the exact blueprint for how we secure these massive, totally unique socio-technical environments.
Which brings us right to Section 1, the hidden danger of smoke. To defeat this incredibly fast-moving threat, engineers have to build what is essentially an invisible architecture directly into the station itself.
Let's compare the old way with the new way. In a standard office building, we rely on passive compartmentalization. We literally just shut heavy fire doors and put up thick walls to box the fire in. But in a massive, multi-storied transit hub concourse, walls and doors are practically impossible. You can't just block passenger flow like that. Instead, the Intelligent Hybrid Smoke Management System, or IHSMS, uses dynamic architecture. When an alarm triggers, motorized smoke curtains instantly drop from the ceiling to form these localized smoke reservoirs. It's a completely dynamic, on-demand line of defense.
But of course, a transit hub isn't just one giant open room. Welcome to Section 2, Defending Different Transit Zones. We're going to take a spatial journey to see how this system deploys hidden shields in every single corner of the station.
Now, what's really interesting about this slide is how methodically the system categorizes the building into distinct battlegrounds. Notice how a large open concourse has a totally different safety objective than, say, an enclosed stairwell or a rail platform. The system is entirely performance-based, meaning it tailors its counterattack specifically to the physical geometry and the very specific threats of that exact zone.
For example, take the high-risk ancillary zones, places like the food court or retail shops inside the station. These places are chaotic. They have a high fire load energy density, which just means there is a massive amount of highly flammable fuel packed into a very small space. You've got commercial deep fryers, cooking oils, plus clothing shops jammed with synthetic polymers and textiles. If a fire starts in here, it exhibits what engineers call an ultra-fast T-squared fire growth rate. So the fire practically doubles in size every few seconds. It literally explodes, producing dense, highly toxic soot. The moment this happens, fast-acting motorized fire and smoke dampers snap shut, totally isolating the zone of origin before that toxic cloud can spill out into the public areas.
So, we've locked down the retail zones. But what happens to the air in those massive, multi-story open spaces? Let's look at Section 3, the architecture of airflow.
Transit hubs are built vertically. You've got underground tracks, ground-level ticketing, elevated buses. This layout creates a really dangerous phenomenon called the stack effect. Just like a giant chimney, the natural buoyancy of hot air pulls smoke violently upward through escalator shafts and vertical voids. To fight this updraft, the IHSMS uses multi-zone pressure tracking and barometric bypass dampers to actively balance the pressure between floors. It forcefully stops the smoke from just riding the escalators up to the ticketing halls. And this brilliantly illustrates the brain behind the brawn. Human intervention during a fast-moving crisis introduces deadly delays. So the system actually relies on a hardwired building management system using matrix-programmed logic. The absolute instant a detector triggers, it executes these 4 steps flawlessly. It pinpoints the origin, blasts the emergency exhaust fans in that specific zone, chokes off the fresh supply air to literally starve the fire of oxygen, and immediately spins up pressurization fans to protect the adjacent clean zones. It is cold, calculated survival logic at its best. But here is a seriously genius piece of practical engineering. Installing massive, dedicated exhaust fans that just sit around doing nothing for 20 years is incredibly expensive and takes up way too much space. Instead, the IHSMS utilizes dual-purpose HVAC. It uses variable frequency drives to instantly hijack the building's everyday air conditioning network, transforming it into an aggressive, localized emergency exhaust system. It's just an incredibly clever, cost-effective structural move.
Okay, we have the technology in place, but now we have to introduce the most unpredictable variable of all in Section 4, surviving the crowd.
During morning peak hours, the population density in these hubs hits an extreme 3 to 5 people per single square meter. Think about how shoulder-to-shoulder packed that is. Because of this extreme congestion and bottlenecks at the stairs, immediate and rapid evacuation is physically impossible. It's just going to take a long time to get everyone out safely.
So, the crucial point is this. The system doesn't actually try to remove all the smoke immediately. That is a completely lost cause. Instead, it prioritizes tenability. It extracts just enough smoke to maintain a clear layer of breathable air greater than 2.5 meters above the floor. It literally keeps the deadly toxic cloud hovering right above everyone's heads for a sufficient duration so the packed crowd can evacuate without suffocating.
And as that massive crowd inevitably moves to the stairwells, they are actively protected by positive pressure containment. The system pumps clean, high-pressure air directly into the enclosed egress stairwells. This pressure creates a literal invisible wall of air that actively pushes out against any smoke trying to sneak in when the doors open. Combined with the fire alarm system guiding a phased evacuation, it prevents deadly panic and bottlenecks by moving people out in very calculated ways.
Let's move to Section 5, combating diverse fire loads, and see how this builds our understanding of what exactly is burning in a transit station. Up in the large open concourses, the fuel load is entirely transient and completely unpredictable. It's brought in by the passengers. We are talking about massive quantities of personal luggage, nylon backpacks, strollers, and commercial promotional booths made of polyurethane. When ignited, these everyday synthetic materials produce incredibly high smoke obscuration rates, meaning impossibly thick, blinding smoke. The system handles these sudden massive fuel spikes by dropping those ceiling curtains we talked about earlier to capture the cloud in a reservoir.
But down on the track level, the danger changes entirely. The operational core of transit platforms is just packed with heavy, high-voltage electrical distribution networks and signaling equipment. These heavy industrial cables are insulated with plastics like PVC and XLP. If an electrical fault occurs down here, the incomplete combustion releases extremely corrosive hydrogen chloride gas. This isn't just smoke anymore. It is a highly deadly chemical threat.
In the ultimate nightmare scenario, it's the rolling stock itself, a diesel bus or a multi-car commuter train catching fire right inside the station. This creates an exceptional peak heat release rate from burning mechanical lubricants, electrical wiring, and composite paneling. To defeat this absolute worst-case scenario, the system fires up massive reversible jet fans to create a high-speed longitudinal airflow, aggressively sweeping the smoke down the trackway tunnel far away from the station. Simultaneously, it relies on platform screen doors, those glass walls separating the platform from the track, closing tightly to act as a physical seal. It traps the toxic smoke inside the track void while passengers evacuate to safety.
Now you might be wondering, how do we actually know this massive, complex matrix works if we can't safely set a real fire in a crowded station to test it? Well, first, engineers rely heavily on computational fluid dynamics modeling during the design phase to simulate the physics. And once it's actually built, the building management system runs automated low-speed diagnostic self-tests every single week on all the dampers and fans, quietly verifying the invisible security net without ever disrupting the daily passenger flow.
We walk through these massive concrete and glass cathedrals of transit every single day, mostly completely unaware of the dynamic, automated forces engineered specifically to protect us. The ceiling curtains, the pressurized stairwells, the reversible jet fans, they are all just waiting there in silence. So I leave you with this. The next time you're standing on a crowded platform waiting for a train, will you look up and spot the invisible architecture keeping you safe? Thanks for joining me on this explainer, and stay curious.